All right. We're going to finish off variational inference today, and then also start discussing another approximate inference technique called Markov chain Monte Carlo methods. Okay. As you can see, the lecture is now into the blue water region. Are getting more and more technically difficult materials. So I highly recommend you to either prep the lecture or you go home and review the material with assigned readings and the slide themselves, because not all the contents can be immediately understood during the lecture. If that's the case, then please do review them. So just a quick recap of variational principles. The first message is that a traditionally probabilistic inference problem or many problems that are algebraic can be reformulated as a solution to a optimization problem. And in the case of a probabilistic inference, here is the variational formulation. We define the solution to, say, our partition function A. Instead of, how do you get partition function usually? Just to make sure that you know the context. Give you a probabilistic model, how do you compute the partition function typically? You integrate or sum over all the random variables over all their configurations, which is usually exponentially complex, right? So in this case, we term the solution of the partition function as a solution to a optimization problem. In this case, we have the inner product of the dual pair and also a conjugate function. And we know that these correspond to the canonical parameters in the exponential family expression of the probabilistic distribution. And the mu's correspond to the mean parameters. In fact, mu satisfy some constraints, which is the expectation of the sufficient statistics, right? And then this A star we derived already correspond to what? The entropy of the original distribution. If you know how to write the entropy, then you actually could reformulate the inference problem on A as this one. And the solution only exists when the mean parameter vector satisfy a constraint, which is that they should be within a domain called marginal polytope. And why they are called marginal polytope? Because it is a convex combination of the marginals, okay, of all these sufficient statistics, okay? And in the discrete case, it's a convex Hall of the linear combination of all that. In the continuous case, it's the real convex Hall of that. So make sure that these are what you should remember. And if you need a real case example, we can look at a two-node Ising model where everything can be, in fact, taken care of analytically. You have the original distribution, and this is the vector of all sufficient statistic. And then you can literally, compute the marginal polytope. Okay, this is a Minkowski-Weil representation of the marginal polytope, which is a collection of the half space. Okay, and this is the entropy of the model. You can actually compute the entropy of the model just using this equation because this is a small distribution, and then you can now compute, express the partition function using basically this expression. Okay, and then you can of course attain the optimum, at like this, okay, by taking derivatives of the objective function and set them to 0, which gets you the stationary point, okay? And we know that you cannot afford to do all this, in many of the complex approximation. And that's why we need to use this formula. This formula is not for you to actually do this, which gets you still the exact inference. It is actually a vehicle for you to do very conscious approximation to a more complex distribution. And that brings us back to the two stories we told in the earlier lectures. We know what is a mean field approximation already. I'm going to quickly review that so that you see how that corresponds to an approximation to this problem. In fact, it corresponds to a certain way of approximating this, where the space of the mu, okay, is now redefined to be a subspace of the true marginal polytope. And that subspace is a lot easier for you to search for a solution. And this A star, which is the entropy of the distribution, is actually also defined as in a certain way that is easy to compute. And what's the other approximation technique we learned so far? The Loopy belief propagation, right? We knew that somehow you run a belief propagation on a graphic model with loops, which is not a tree. You still sometimes get convergence. It is very close to the true solution, and sometimes you don't get solutions. And why that's the case? Well, we're going to examine a little bit about that. And here, you are going to find that, in fact, we're going to define a space for the another different space for the mean parameters, which turns out to be a superset of the marginal polytope. Okay, it's very, very interesting why it's a superset. And then also we're going to approximate this A, using, what is this? Using a approximation. We're going to basically remember that A, by definition, is the entropy of distribution. And the entropy of a distribution for complex distributions is sometimes very easy to write, right? So I'm going to basically replace this with the best free energy. Okay, that's a different as approximation, using a tree technique to define the entropy. So let's take a look about exactly how they look like, the mean field. So here is how the mean field entails. It's basically, graphically correspond to a subgraph, approximation to the original graph. Say we have a graphic model like this, right? Where you define the canonical parameters on each edge, and then the space of the theta is such that they ensure the partition function is bounded. And you can define a subgraph like this. This is a subgraph F0. Well, this is a graph with no edge. Okay, but it's still a graph. It has nodes, right? What does that correspond to? It corresponds to basically a space of the parameters where, when the edges, when there's an edge, we set the weight of the edge to 0, right? And so that means theta ij equals to 0. And what does that translate to in terms of the mean parameter? So for example, we have a mean parameter mu ij, which corresponds to a sufficient statistic defined on the pair of xi and j. When this edge has a 0 weight, what does it translate to in terms of some properties of that mean parameter? Remember, this actually corresponds to what? Corresponds to the marginal of xi and xj, right? And they basically correspond to p of xi times p of xj because there's no edge between them. Therefore, they become independent. Therefore, they correspond to mu I times mu j. Okay? And you can imagine you can have other subgraphs. For example, this is a subgraph where you just remove some edges and turn them into a tree. And that's basically defining another subspace. We are going to talk about that later. But you can always approximate a full original graphic model with a subgraph with some edges removed. That's a graphical approximation. And the graphical approximation translates to a geometric approximation to this, with that, and also to a geometric approximation to the marginal polytope in a certain way. Okay, so that's the key idea behind mean field approximation. So let's think about the mean field more specifically. So for a given graph, trackable subgraph, the subset of canonical parameters basically is basically falling into here. And we should define a new space for the mean parameters, which basically are those mean parameterization corresponding to the theta that is constrained by the subgraph, right? And this actually defines a new subspace, which is known as the inner approximation to the full marginal polytope. Inner approximation look like what? So remember, the marginal polytope is convex. We have the extreme point like this. Say this is a marginal polytope. And how an inner approximation look like? It looks like this. Somehow it must be within. We could actually have a weird shape, but it is within this polytope. That's called inner approximation. Why it is an inner approximation? Just by intuition, why it is an inner? It has to be within. Why? Because this is a subset of the full set of all possible theta, right? If it's a subset, then it has to be smaller. Therefore, you have to be going within from the marginal polytope. Okay, that's the beauty of this intuition. And then, we are going to define now the mu parameters to be in this inner approximation to the marginal polytope. And we are going to now compute also the, the partition function. The dual of the partition function, which is the entropy. So a entropy distribution, entropy of a distribution that is corresponding to a subgraph with no edge. How do we compute that? What does it mean by a subgraph with no edge in terms of changing the joint? For example, I have a joint of many x. And now I'm approximating it using the f, the subgraph f, where there's no edge. What is that? Yes, that's actually the product of little marginals, right? And to compute now, the A star of the theta belonging to F, that basically corresponds to H of a Q, right? Isn't that interesting? H of Q equals to what? Equals to sum of H of every Q of Xi. So you can analytically write down this Q now very easily. In the original graph, if you write a H of the P, it is not possible in a complex model, such as a topic model. So with that, basically, you are going to now solve a much easier problem of this one, where here you have an analytic expression, and here you have an easier subspace. And just to give you an example, for example, here is our easy model. In fact, imagine that it is very big. And then what's happening is that you are going to now define the mean parameters to be basically correspond to this and this. Okay, they should basically be a marginal. And also, if you have a mean parameter correspond to a pairwise sufficient statistic, then they factor into singleton statistic. And that's how the subspace look like. And then this is the entropy of the approximation to the mean field, because there is no edges in here anymore. Therefore, it becomes this graph. And then how to solve that? Well, you take a derivative of this with respect to tau, and you get a pretty straightforward expression, okay, which is like this. Okay, so this is basically how you solve a approximation to the Ising model. And the way you derive an approximation to the topic model and other models using a mean field is exactly like this. Okay, you are going to write down all this subspace and the entropy over factor model, and then you're going to do a very, very simple approximation with respect to optimization with respect to every parameters in the model, and then you get a solution which is usually iterative. Okay. So with that, we just do a quick recap. So this is the geometry of mean field. You have the marginal polytope, which was convex, and then you are doing an inner approximation, and this is a strict subset. And also remember, this inner approximation must be non-convex, because the full space is a convex. Anything that is within cannot be convex anymore, right? And then you have, and this is a analytic expression of a simple case. Okay, now any additional insights you may want to draw from here? For example, are you going to always be, say, converging? Or actually, are you going to get a true approximation, to the like not a true approximation that is equivalent to the original solution? Yeah. There are a number of issues here, right? So the true solutions may be here. You're not going to get it, and also it is a non-convex space. Therefore, you are not guaranteed. You are likely to stuck into a local minimum, just like we do an EM algorithm. Therefore, your algorithm is not guaranteed to get you the optimal, global optimal. Okay, but anyway, it is a simple algorithm that solves a much more complex intractable problem in a iterative fashion. So that's why people like mean field. So likewise, let me say just a few words about the best sum product method, Loopy propagation, before we move on to the new topic today. So just a recap. This is a sum product algorithm. The key equation here is that we have a message passing protocol, and we've done a lot of derivation already last time. That it corresponds to minimizing what we call a best free energy, right? The best free energy is just a hand kind of crafted and hard-coded definition, which is built on pairwise sufficient statistic, pairwise marginals, singleton marginals, and also the degree of every node in the graph, right? I don't have I may have a equation, a definition somewhere, but so these are basically a tree graphic model where the approximation is actually exact. Okay, well, we shouldn't say the approximation exact. The approach gets you an exact solution. That's because in tree graphic model, the way you define basically the marginal polytope is actually the true polytope, where you need to satisfy what we call a local consistency, the normalizability of the mean parameters, and also remember this one. This is the pairwise marginal. And when translates to the space of all possible mu's, we basically can introduce these two types of constraints, right? Which basically gives you the local consistency guarantee of the marginal of the mean parameters. Now, these local constraints leads to global constraint when what happened? When the model is like what? When the model is a tree itself, then these constraints are all you need to guarantee global consistency. Right? Remember? But when the graph is not a tree, like this, then local consistency does not necessarily lead to global consistency. And then if you want to still use this, you are going to get an approximation. Okay. And then we have a number of additional technique where, for example, in order to still treat the problem as a optimization problem, we need to now define the A complement. And we know that it is correspond to the entropy. And for a tree, how do we define entropy? Using pairwise statistic and the singleton statistic. Well, this is what we derived last time. We basically could have a very simple definition like this. Okay, and then given that we are going to define the mu in a polytope that is defined by local and global and pairwise local consistency, and also the loss function here to be defined by an analytically derivable entropy function. Then what you, at the end of the day, do is to solve this Lagrangian, and then you get basically the solution to all the mu's. The mu's correspond to xi and also xi and j. Right? And these are some algebra which basically gives you, the solution like this. And if you recall the slides from last slide, right, this actually corresponds to our cluster message and the singleton messages. Once you redefine this Lagrangian multiplier in the form of a message into or out of a factor. Okay. So what's happening here in terms of our variational formulation of the inference problem? What we just did actually is inspiring another variational approximation, okay, or approximation to the variational inference formulation in here. So this is how we define, the variational expression of inference, and we need to basically take care of the form of this, and also need to write down this part. And in the mean field case, we say that we are going to introduce an inner approximation to the marginal polytope, because it is only defined by a fully disconnected graph. Now we are going to approximate M using this one. Only the local consistency. We basically say that for all the mean parameters defined on sufficient statistic, we are going to ensure local normality, singleton and pairwise normality, and also the local consistency to next to it. And we don't care about whether they are global consistency or not. Okay. So this is a space of the mu. Now I ask, do you think this space is smaller, equal, or bigger than the marginal polytope? Why smaller? Here you forget about the tree because I'm not talking about the tree anymore. I'm talking about using the tree to inspire some constraints, right? But there are other constraints I don't care, basically. Yeah.
Bigger, it has like less constraints.
Yeah, that's the intuition. You have now less constraints, right? There are some other constraints which are global, which I don't care with. I don't capture here. So without even figuring out how what they are, you could already kind of have a rough assessment that it must be bigger. Then when it's bigger, how it look like? It look like this. Right? It is outside of that. So it is called the outer approximation to the marginal polytope. And then we still have the problem of writing down this. For an arbitrary distribution of this, given arbitrary distributions, writing down the A is going to be very complicated, right? And what I'm going to replace is to really approximate this with a best free energy, okay, which is, you can find the definition of the best free energy last time. Basically, only requires you to use pairwise statistic and the singleton statistic. Okay, so that's basically what is a variational approximation look like. You are essentially doing a outer approximation to the space of the main parameter, and then you are replacing this A star with a approximation to the true entropy. Okay, you use the best entropy to approximate the true entropy. So this is to contrast in mean field. If you still remember, in mean field we are introducing an inner approximation to this one, and we are writing down the true entropy, okay, of the Q. Okay, and why we can do that? It's because we explicitly express the approximation of P with a Q here. We basically explicitly write that Q down, and the Q is a factored form of little q's. And that actually inspired all this to be also expressed. In the best free energy thing, in the Loopy belief approximation, I didn't actually even show you how an approximation to P look like. There is never an explicit expression of that. I only ask you, what do you care in terms of query? And the query that you care about is basically expectations of the singleton and the expectations of the pairwise. Right? And I don't care basically, what else lies in this whole full distribution. So I'm going to treat these two things which correspond to the mean parameters and of singleton and pair directly, and I define a space based on the local constraint, and then I define the approximation to the entropy only using these two types of statistic. Okay, so I bypassed the explicit expression of the P, but I know it is approximation because we knew that the full distribution have more edges and actually have a lot more structures in the entropy. We just don't care how they look like anymore. Okay, so that's basically giving you the geometry of the belief propagation, right? You actually now are approximating with an outer approximation. And we also know a reduction case. If the distribution is a tree structure, then they are exact because this one become equal. And also the best free energy is exact to the true energy if the distribution is a tree. But if it's not a tree, we know this become all approximate. And we know also it is approximate from outside rather than from inside. Right? Okay, so that kind of gives you, some insight about the behavior of the belief propagation. First of all, it may not converge, and also it may not converge to the right answer. Why? Because, for example, if you converge a point into here, which is within kind of the space of the outer bound and the marginal polytope, then it is not a true mu that is realizable, but your solution can still converge there. So in those cases, you are going to get a bad answer. Okay, or sometimes it will oscillate between different solutions because the space is not necessarily even convex. Okay. And here I have a few examples of the approximation, which I'm not going to discuss in detail. But just in summary, now we see a optimization theoretic approximation to the intractable inference problem. And remember these two, Kikuchi, which I don't want to cover anymore. It's a classic technique also invented by physicists, which allows you to do lower granular approximation by defining something called a Kikuchi free energy that is a little bit more accurate than the best free energy. But rarely people now use this technique, so I'm going to pass that. So with that, I'm going to close this part and move to a different lecture, which I believe is doable today. That is also very important, which is based on sampling technique. Okay. And again, just give you the big picture. We know how to do exact inference, and it applies to certain tractable graphical models. And then the two major family of approximate inference are variational and the stochastic sampling. And we're going to start today with this topic. So go back to our inference problem. We have a true distribution, and the inference problem correspond to what? Right, correspond to, for example, producing a marginal, okay, or sum over, or maybe computing the partition function. It also could be even more elaborate. Once you have you want to have a function defined on either a subset or odd x, you can compute the expectation of that, which amounts to an integration, okay, of the given function over the probability distributions. And if you look carefully, these three operations are very similar. It's about, in some way, sum over all the configurations of your random variables, okay, in certain context or in no context. What is a sample-based representation of that? So it goes like follows. Suppose that you have typically when we are talking about distribution, we may think about some nice shape like this, which has a beautiful closed form expression like Gaussian, right? And then you integrate it. But what if you have a rather annoying distribution like multimodal like this? Such distribution exists, right? A mixture model could give you a density like this, right? What could be another way to do it? Well, sometimes integrating a P like this may be not feasible, but people can use a random number generator to draw samples from this distribution, right? That's something that you probably are quite comfortable with. And I suppose you know how to draw a sample from a simple distribution, say a Gaussian distribution. That's in R and in my lab, it's a single command. But of course, there are little dirty tricks behind the little command, which actually use a uniform random number generator between 0 and 1 and somehow transformed so that they behave like Gaussian. I'm not going to cover that. So you do this, and then once you do this, can you actually rephrase this problem? Well, here is how we would do it. You draw now a sample, say, from a distribution, and you draw it, say, capital N times. And once we have n examples of data points from this distribution, how do we compute this one, which was an integration originally? You can just plug in the x right into the equation, sum over it, divided by n, right? So in a sense, your original distribution P is now expressed as a set of samples. Okay, that's just a very simple idea, very intuitive. Well, that's really what Monte Carlo methods is about. It has a fancy name, Monte Carlo, because of some gambling historical context. But the gist is that you are going to replace the integration with a summation over samples drawn from the distribution that you are interested in. Then, in fact, there is also a beautiful theorem saying that if your sample gets more and more until infinity, you are going to get infinitely close to the true answer. Okay, that's why we call them asymptotically exact. Okay, so all so beautiful, right? Maybe it's too good to be true because it looks like we don't need to worry about all this variational stuff, right? And we just draw samples. So in reality, there are some challenges as I listed here. How to draw sample from a given distribution, such as the distribution like this? Well, we know draw samples from a discrete, like binomial, multinomial, or from a Gaussian, or maybe sometimes student T distributions and other things. But how to draw sample efficiently from an arbitrary distribution? I don't think people have a good answer to that. It's all case by case. Okay. And also we say how to. Some samples are not very useful. In fact, you will soon see that not all the samples are equally useful, and therefore we need to make a better efficiency, in terms of using a sample. And also, this word asymptotic is very mysterious. It means that you want to get more, the more the better. But obviously, we have a finite lifespan. How many samples we have to draw before we stop and hand the answer to some people? Should it be 100 samples or 1,000,000 examples or more? Right? So all these actually are questions hiding behind the Monte Carlo methods. And I will give you one example to really highlight the difficulties I just mentioned. Okay, so let's say we have a joint distribution here. Maybe we just gave names to it. This is a network telling you a story. Okay, we have 5 random variables, and we're going to have a joint distribution, xa all the way to xm of that, and a particular sample correspond to basically a whole slide, okay, of examples like xa to xm, x capital M. And these are the index. These are just the name of the random variables coming from P of x. Okay, so how do we draw this example? Well, you have a naive way of drawing the examples from distribution. You can draw by traversing the graph because it is a Bayesian network that factors. Therefore, this whole thing corresponds to P of, say, A given B and E. Of course, it has to also have a P of B and P of E and so forth. So what you can do is to read each of these local marginal or conditional tables and draw sample one by one. Let's say we draw the first example. We have a distribution that is highly biased. Burglary is unlikely to happen. It's having only 0.001 probability of happening. So you draw an example, what sample you are likely to have. You may have a E0, which means that not happening. Okay? And then you draw this. Earthquake is also very rare. And you draw earthquake. Oh, okay, I just write B and E. So these two are, say these two examples give you both 0 value. And then conditioning on E being 0, B being 0, you index into this conditional table, which row I'm going to use to draw the next example. False, false, right? That again gives you a very low probability of alarm, okay, goes off. And naturally, you sample once and you get A equal to 0. And then given alarm is off, you are going to sample whether J, John calls or Mary calls and so forth, you get all 0. Okay, so that's how you get one piece, one sample, okay, from a distribution. Then you do it again, you get the second example, like this. And then you do again, you get the third example like this. In here, something magic happens. Suddenly you draw this example, J equals to 1 and so forth. So you can keep drawing. Right? Now you draw 10 examples like this. And you want to now use them to compute your inference query. Say I want to do a query where, say, what's the probability of John makes a call or not, given that the alarm is not going off. How do you typically do this query? Well, you are going to, first of all, check those samples where the condition is met. Right? So you look at this whole row and how many times the alarm is not off. Well, you have this 9 examples. And then you also need to get all those samples where John actually made the call. And that's actually correspond to this green example. Right? So 1 out of 9 samples, you see this event, you are likely to compute the probability accordingly like this. Okay? And of course, you could also see some other configurations in here, but this configuration is not consistent with our conditioning evidence. Therefore, I'm going to discard it. Now going to another query. What is the probability of John makes a call when the alarm is off, or is on? You go through the samples again, and fortunately you saw 1 example in here. And in this particular case, John actually made a call. So the probability you are going to compute actually gives you this. The conditional likelihood of J given A1 is 0 and 1. Okay, he definitely will do something basically. That's because of what the sample tells you. Okay. So any problems already until now? It's a little bit too biased, right? And why it is so biased? The sample is too small. Sample size is too small. I only see 1 example, right? And why it is too small? Because the probability actually naturally generates samples like that. They are rare events. They are rare events. Therefore, when I sample them, I don't get the samples very often. Therefore, when you're conditioning on rare events, then you suffer from this sample deficiency naturally, right? In fact, there are also queries where you may suffer 0 examples. There are no examples that in your samples that reflect that condition. Then you cannot even begin with a computation, right? So that gives you some kind of ideas about why a trivial sampling method isn't necessarily working, because you basically very often run into cases either the sample is inadequate or the samples are many but they are not very useful. Okay. So Monte Carlo technique is a collection of techniques which is trying to circumvent the problems I just mentioned, and here is a list. Today, I think we are going to cover the first, 3 methods. Okay. One method is very, very natural, which is known as the rejection sampling method. Okay, and here is a target distribution I want to sample. And let's be realistic. In fact, the target distribution may be complicated, therefore, such as Markov-Random field. Therefore, I don't actually even know the partition function, but I can always, know the energy function on top of it, or the potential functions on top of it, and they can be easy to evaluate. Right? Evaluate means that what? Means you plug in the numbers, replace the zero or the x with the real numbers, and then you can compute a value out of it. So rejection sampling tells you the following. You are going to now draw a sample from some distribution Q, okay, and then you are going to do one more step, which allows you to accept or reject this example based on this number. Okay, it's the ratio between the unnormalized part of the given distribution over a constant times, that sampling proposal distribution. Okay, and I claim that with these two steps, you are going to get x star actually coming out of a pi x. So how do we prove? In fact, graphically, graphically it's here, but I'm going to explain that later. How do we prove this? Do you believe what's happening here? Let's do a quick proof. Okay, so we worry about x star, and we want to really prove that this probability defined by these two actions allows me to establish that this x is coming from this distribution. Okay, how do we do that? Well, the first step tells you that this p of x star must be equal to q of x star, right? And it should also be proportional to pi prime of x star divided by k of q x star. And by the way, this is not even normalized yet, right? Then we basically just normalize this distribution. Okay. Yeah.
Our simpler distribution has to have full support yet.
What's that?
Our simpler distribution has to have infinite support yet.
The sample distribution is any distribution that you feel easy to play with, like a Gaussian distribution or whatever.
Sure, but I mean, we're ruling out like degenerate ones that say have one sample of probability one yet.
I don't understand.
I'll ask.
Also technicality, you are talking about the difference between density and the probability and all that, right? Yeah, but that's a technicality. Imagine it's a discrete. Density, you can always replace them with a integral or whatever. Right? So once you have this, you can do some canceling, right? And the k is also here and here. So this equals to what? Right? Yep. K is any constant. Just imagine there's any constants that exist, which allows this to be always within the range of x, 1, and 0. Right? Because you don't know the value of this, you can always imagine there is a max value somewhere there, but it's always dominated by k of q. Okay? So what does this equal to? Pi of x. That's it, right? So magically, in this two-step sampling procedure, you generate a sample that gives you the probability of the original pi of x. I have some cleanup notation of that. Okay, so that's basically a solution to sample a hard to normalize distribution using a what we call a proposal distribution queue. So any pitfall with this technique? Yeah. What's that?
You can be rejecting the samples most of the time.
You can, yes. And when that happens? Yeah, for example, this can happen, that you are having a weird distribution, which is like this. Like this. It has this little spike here. Okay. Therefore, to satisfy, the validity of the k, you need to basically have a proposal and then elevate it to this, so that it has to dominate your true distribution. At any point, you have to dominate that. Otherwise, you will be in a region where this probability is, this rejection proposal is poorly defined, right? So if that's the case, your sample basically come over all the space, under this proposal density. But what other space that can be rejected? Well, these are the space that will be rejected. Yeah, and that's why you are going to have a lot of rejections, right? And that's no good. Okay. In fact, here I have an example, which is kind of an artificial example, but to give you a sense about how wildly wrong you can go, if you use a naive rejection method. And I'm going to basically have a target Gaussian distribution. Just for fun, I'm going to use another Gaussian to sample this Gaussian, to approximate this Gaussian. Okay, this is a conceptual experiment. You don't do that because you can already sample from Gaussian. Why do you approximate that with another Gaussian, right? But it gives you a sense about how, even small differences, between the two distributions caused by that normalization or this scaling constant can cause a big difference in the rejection rate. So, you can imagine the true Gaussian has a p, a variance, and my proposal has another variance, and they are different only by 1%. And remember that what is the definition of Gaussian, right? It's basically equals to 1 of, I think, epsilon 1 to p to square, and then exponential of something like that, right? Therefore, you could already calculate that k, which is measured by the ratio of these two elevated to the power of d, which is the dimension of the Gaussian, could be this big. Okay. Therefore, you can say that the actual volume of these two distributions are vastly different in the in a high dimensional space. Therefore, you are going to reject your samples most of the time, even though the two distributions are so close to each other. So what people do are different ways of fixing this. Maybe I shouldn't just cover the whole thing with one distribution. I'm going to use a piecewise envelope to kind of cover a target distribution. But these are quite complicated. Okay, so that's about rejection sampling. A simple method, but it didn't work very well in the high dimensional space. And then comes to the next idea. It's called importance sampling, and there are two versions of the importance sampling. And the idea is the following. So I'm going to now still draw example M from a Q distribution, a proposal distribution. And instead of rejecting and accepting those examples using the proposal I just mentioned, I'm going to now compute a weight of M based on the probability ratio of this new sample under the target distribution and the proposal distribution. Okay, and as a record, I'm going to keep both the sample and also the weight as my representation to the true distribution. Okay. So that's the first idea. You may worry that now why I start to assume P is suddenly available. I'm going to take care of that later. Okay. In here, I assume in the simplest case, P is evaluatable, even up to a normalization constant. And so this is like these two distributions like this. And how to show it is correct? Well, here I have a again very simple proof, and you want to actually now know the tricks in this proof. It's very simple. You want to calculate a expectation, and you introduce two dummy terms, okay, in the denominator and the numerator, and which are corresponding to your proposal distribution. And therefore, your integration now becomes these three parts. And to replace integration with sample, we basically now replace this with the samples. And this actually is exactly our weights. Therefore, you can now re-express this one like this, right? And that gives you basically finally this formula, which is exactly our important sampling entails. And here, why I call it anomalized, because these weights are directly computed from electrical ratio. They don't normalize to each other. When you add all the weights together, they don't sum to 1. They can be any positive values. But it gets you a first approximation to the true distribution. Okay? And then comes to the immediate question, what if I can only evaluate my proposal and my true distribution up to a constant? For example, I don't have the exact value of the normalization constant, therefore I define them to be a alpha, right? And I can evaluate only the unnormalized part. If that's the case, you can still define a ratio, okay? And then you can actually see the following thing. It's very interesting. Let's compute the expectation of the ratio itself. Okay, this ratio is between the unnormalized target distribution versus the proposal distribution, and you compute a expectation of that. And that gets you basically the expectation of the ratio is corresponding to the normalization constant itself. Okay? And that's quite interesting because that means this constant, even if you don't know its value to begin with, you actually will have it once you have all these ratios. What you do is to now compute a expectation of all the ratios. How to compute that? Well, basically you have Rm divided by the sum of all the Rms. And that basically gives you this value. Okay? All right, so that's a new procedure. What's happening is that you are going to now draw M from the Q, and M equals to 1 to, say, n examples. And once you achieve an example, of course, along the way, you can always compute the little r's, okay, for each of the m. And then after you've done, you are going to now just compute a alpha, which is the sum of all the weights. Okay? Get that? Actually, here I made a mistake. What is how we compute alpha? So by definition, alpha. Yeah. So in fact, I'm going to go back to this equation. This is exactly giving you how you compute the alpha. It's basically this one is R and normalized R's, of M, right? And here they are going to be expected over Q. Then you just expect, all the replace basically the X with the XM, and then you sum over it. That's it. Right? That's why alpha equals to the sum of all the weights. And again, we can make a proof about the correctness of that. You are going to now compute the expectation, of a given function using samples drawn in this manner, okay? And they analytically can be expressed by this integration, and we express the P, using this and that, and then we introduce a pair of Qs, and that gives you, this little r in here. And then that also gives you this alpha, which is in the denominator, and the Q, where you draw sample from. Okay? And then once you have this equation, you are going to now replace everything with samples. So this Q of X are now replaced by the samples from Q coming from here. And where the sample goes, well, they go to everywhere that X appear. Therefore, Fx becomes F of Xm, okay? And this little weight R is going to be now defined by Rm, which is the weight or the ratio due to sample m, and then in the denominator you have a sum of that. Okay, so this part is now giving you a normalized form of the weights. Okay, every weight divided by the sum of that. Therefore, you can also compute, the weights after you have every examples. So at the end of the day, what you are going to keep are X of M and W of M as this. And then when you are doing the inference, such as an integration or an expectation, you are going to basically plug in the samples like this. Okay, so this is called the normalized importance sampling, where you don't need to know basically the partition function or the nominal constant of a target distribution. How good they are? Well, there are some nuance in terms of the asymptotic accuracy of these two distributions. I don't think I want to discuss this here. You can go home and read about it. One is a biased, meaning that it's going to give you asymptotically a true expectation, which correspond to P of X. And here, we can also show that it is not necessarily correspond to P of Fx under any finite sample. Okay, and the proof can be established once you just plug in, say, one example or two examples. But I'm going to skip that part. It's not very interesting. I want to say one more word about what we have so far. So the algorithms that, did I have that? Okay. Yeah, so what we've seen so far are basically based on likelihood weighting, and the likelihood weighting is very simple to operate, but sometimes it's still hard to get you to the true answer in some peculiar scenarios. So let's imagine a distribution like this. So for example, when you practically run MCMC, when do you stop? Well, typically people say, I stop when I start to see stability and convergence. In any iterative algorithm, including sampling algorithm, that's a empirical technique, to control the duration of the iteration. But in a more technical way, it is equivalent to say that when my estimate of say when the answer to my inference problem becomes less variable, it's becoming low variance, then I'm going to stop. Because I don't know the true answer, right? You're trying to compute a true answer, therefore you don't actually know when you get the true answer. You can only guess by saying, when I iterate, my kind of current answer start to stabilize and show less variance, then that's likely to be a true answer. That's usually the nature of a iterative algorithm. So then the stability of the variance of the outcome hopefully can reflect, your closeness to the true answer. But in what I just said, in the importance sampling, we could run into the following case. Let me just cook up an example for you. So let's imagine we have a target distribution. Something like this. Okay. And then I'm going to also have a proposal distribution. Say green one, blue one. Well, for multimodal distribution, to choose a proposal, you don't have too many options. Usually you choose a Gaussian distribution or something, right? And if you are not very lucky, you may choose a proposal which is like this, which is obviously not very good. But on the other hand, you don't really know it, right? And then you are going to start draw examples. Say you are going to draw examples in here and here and here, and very often a lot of examples in here and here and here. Some examples in here. Okay. And your weight, okay, either normalized weight or unnormalized weight, is going to give you a importance of every example. So, for example, you are hoping, even though these examples, the ones in here, are, not, often to be drawn because it is in the tail of my proposal, but once it's drawn, it's going to receive a pretty high weight, right? Because it is, after all, in the high density region of the target distribution. You are hoping that weight can correct you. So this weight can basically be able to correct, the value of every sample. But you also could run into a case where you are having so many examples from here, okay, and they are overwhelmingly more than those examples. And then when you compute the weights, you actually see a lot of weights coming from here. They are all very small. But because you don't see these too often, or you don't see them ever, you don't realize that they are small. Okay, especially in the unnormalized part. In the unnormalized part, you actually you are going to only determine the value of the weights by summing over all the weights and reweight it. Therefore, when you see the weights itself, it is not telling you how important every example truly is, right? They can only tell you how relatively important they are. Then imagine that if you are drawing too many samples from here, you are likely to see a convergence of all these little weights, okay? And so that your weights are actually not changing too much, but you are still in this low density region, and you are off the target. Okay. So that's actually something people from time to time run into, okay? And in fact, I have a more clean graph in here. And if that's happening, what can you do? Okay. So somehow, because in the computer program, the way you monitor convergence is really not to plot all the points like this. You are going to just monitor the average of all the weights and see whether they change or not. If they don't change, you stop. So that basically causes you to miss some of the high density region. So what we are going to prescribe is a new idea, which in fact there are two ideas that you can use. One is to really impose a heavy tail queue, meaning that you are going to now have a queue that is like this, very heavy tail. And then what's the problem? Many samples are wasted, right? They're going to get low weights, and they're not going to be used. And then the other idea is to do weighted resampling, meaning that you are going to now keep these normalized weights. And originally, we say that we are going to have XM and WM, and we're going to keep them as the set. But what you could also do is to now write down all these Ws, okay, and 1 up to n. And you're going to resample from this vector of weights. Say you draw a weight from here, and then you are going to now pull back the x into here. And next time you are going to get another xi. But for those weights which has a higher relative value than others, chances are you are going to, by the way, the resampling, okay, resample is going to be done for n prime times. It's not going to be n times anymore. Okay, in fact, this n prime is going to be much, much larger than n. Okay, you have only 100 examples, for example. You are going to use this 100-dimensional weight vector to draw, say, 10,000 instances. Therefore, some of the high weight examples will be redrawn many times. So I'm going to now almost like amplify these distributions and dwarf these distributions, okay, using the resampling scheme. Okay. So that's called the weighted resampling. You are going to sample twice so that you get the original seeds. The seeds are getting reweighted, and then according to the weights, you're going to resample those seeds so that their density gets a augmentation of that. So with that, I'm going to quickly show you another algorithm known as particle filtering. That is literally using the resampling idea to allow you to do very, very efficient and elegant, sequential inference. Okay. So the goal here, is to make a fast sampling-based inference algorithm for this model. We know this model already, right? This is the state space model we do. We have a common filter algorithm already working on that. But sometimes, common filter can be quite demanding to implement, especially in the high-dimensional space, or maybe the transition model is not Gaussian. Then you need to do Taylor approximation and other things, right? So here, let's see how a sampling algorithm is going to deal with that. Okay, so we're going to now draw samples. We're going to construct weights, and we're going to, resample. Okay, all the new examples from these weights, and let's see how that gets you to the right answer. Okay, so starting point is the following. We still, use the same idea we studied in common filter to establish a recursive procedure. Let's say that we have this, which is a conditional distribution of the last state x, okay, given the evidence up to here. Okay, and how to express that? Well, here is the first thing. You can hopefully prove to yourself that I can have a way to break down the expression of xt given y1 to t into this expression. Okay, maybe I should copy down how exactly you can do that. Or maybe I should not. Do you want me to copy down? Right, so basically, the decomposition of this conditional distribution is now to x of p of x given y of 1 to t minus 1. Okay, basically, there is a xt here, there is a yt here. I'm going to now separate this part and that part into two expressions. Okay? And then they are normalized in this way. Okay, so if you inspect this, this is a distribution. And I can come up with a sample-based expression of that. Let's replace this expression of the conditional distribution, which is x given the partial sequence right before x, okay, to be a proposal distribution. I use that as a proposal distribution for this one. Okay, I can draw sample from here. Once I have sample from here, then let's look at this part. This part now is expressed as a weighted samples, right? So this distribution now can be expressed as a reweighted samples from a proposal distribution of this. Okay? And our goal is to now allow inference in the form that if we know this already, know this means that we have all the samples and weights like that, how can we move into the next one, xt plus 1 given y t plus 1? How do we do that? Okay. So it's very interesting. So let's see. First, we want to do a time update where we can keep the evidence and only until 1 to t. And then we're going to add one more time point in the hidden states. Okay? And this can be expressed, as a product of the previous, the previous, conditional distribution of the hidden states given the full sequence times a transition probability, right? And this is this. We already know that. We have a sample expression of that already. And this is, a given form. You need to define a model with a transition probability, so it's given. And so now then we replace this integration with samples. Therefore, this guy is now replaced with the samples. We plug in, okay, and also with the weights. Therefore, it becomes the weighted sum of this transition probability conditioning on the samples of the previous states. Okay. So if you look at this, this looks like a mixture model. This is a simple distribution of a one-step transition conditioning on a particular sample value, and then this whole conditional distribution is weighted by that weight. You can easily sample from this mixture model. Okay. And then we are going to bring the new evidence, okay, and so that we are going to define the next conditional distribution of the hidden states given the full states, given the full evidence up to one more time step. And we know how to express it already. It's basically in here, right? And if you look at that, this involves this part, right? Which is exactly this. This is this. Therefore, since we draw sample from here already, therefore this term can be replaced by samples. Okay? And then this term are what? Well, these are, again, weighted samples. You're going to plug in those x examples, xt1 examples from here into all these terms and compute these reweighted weights, or the renormalized weights. And then you're going to now get a new set of examples, which are newly weighted, okay, for the next time step. Yeah.
In time update, what are the weights?
The time update, the weights are coming from the previous time step. Okay, so where does the weight come from? Well, it comes from the definition of this distribution. This distribution, this distribution, okay? This one is the conditional of the hidden states for the previous time step, right? And they are given by this already. You start from this part. And it's jointly expressed by sample and their weights. Therefore, you need to plug in both the sample and the weights like this. Okay? And then you're going to use this to turn them into new samples and new weights. I have a graph for that hopefully makes the whole thing more explicit. So this graph is kind of interesting. You started from xt given yt, okay? And look at the shape. You have samples and also the size of the ball, meaning their corresponding weights, okay? And then what you're going to do is to resample, okay, your stuff from these weights. And the bigger balls gets more samples, and the smaller balls gets one sample. Therefore, you are going to get now this new sample set, okay? And then you are going to now multiply them with this new evidence, okay, which is in here, that defines the new weights. Then you basically are now going to multiply them with new weights. Okay? Get it? Your sample, so maybe starting from here. Here are your samples, and then your weights. You resample it, and then you are going to reweight it. Okay? So that's called particle filtering, which is using the weighted resampling method to basically keep track of a evolving distribution, because you do this from the current time step to the next time step. Therefore, you can always have a updated online result for the predictive distribution. And the same technique actually, why this is interesting, because it allows you to now draw samples from more complex distributions, such as a switching stasis model where you have multiple slides of the hidden states. And then what you need is basically a way to really sample from all these hidden distributions, which using single transition probability, and also keeping track about the weights and the samples from the hidden states in the way I just mentioned. Okay, I think that's all we should cover. There's a last technique called the raw black virialization. It's pretty trivial. You can go home and read just these slides, which explains the whole thing. Basically means that if you have a long list of random variables to sample from, you can sample only a subset of that. If you know, given that subset, the rest of the random variables can be computed analytically, then that's fine. Okay, say you have a joint case of both continuous Gaussian distribution and the discrete multinomial. You can drop multinomial, and then given the multinomial, you can integrate the Gaussian. Then that gives you a better way to compute the expectation than drawing samples for the whole set of random variables. Right? Yeah. So basically, it means that the integration and the sampling doesn't have to be all or nothing. Okay, you can basically choose anywhere in the middle to combine sampling with closed form integrations. And that gives you some benefits in reducing the variance of the distribution. Okay, with that, I'm going to wrap up the first part of the Monte Carlo methods. And next time, we're going to discuss advanced technique in Monte Carlo sampling methods.